You are looking at the Hong Kong-Zhuhai Macau Bridge. The most interesting part is not its length, but its depth. Right in the middle of the ocean, the bridge suddenly disappears underwater, turning into a 6.7-kilometer tunnel. This tunnel connects two giant artificial islands, the East Island, sitting at the gateway to Hong Kong, and the West Island, connecting to the bridge leading towards Zhuhai and Macau. It integrates these three economic regions, while still keeping the sea surface above open for ships to pass. But why? Why did engineers choose this complex plan instead of building a bridge all the way? And how did they install concrete blocks weighing millions of tons at the bottom of the sea? Let's find out. To understand this decision, we must look at its special location. This place sits right between China's busiest shipping lane and the Hong Kong International Airport. This creates a serious spatial conflict. On one hand, the bridge needs to be very high for giant cargo ships to pass underneath. On the other hand, the bridge needs to be very low to avoid hitting planes taking off and landing right next to it. They could not build high and they could not build low. The only solution was to disappear underwater with a tunnel. Once the tunnel was decided, the next question was, how? Normally, for tunnels this long, the number one choice is always using a tunnel boring machine, TBM. These are giant underground digging machines considered the safest method in the world. But for this project, the engineers were forced to reject that method. The reason lies in the mud. The seabed here is a layer of soft mud, 30 meters thick. A heavy TBM would easily sink and get stuck in this sloppy mud. At 40 meters underwater, you cannot dig a rescue shaft to pull the machine out like on land. If the machine gets stuck, the project is over. The risk was too big. So they were forced to choose a more difficult method, the immersed tube, which means building tunnel segments on land and then dropping them into the sea. However, you cannot place a tunnel weighing millions of tons directly onto that 30-meter thick mud layer. It would sink unevenly and snap in half immediately. Therefore, the first step the engineers took was turning this sloppy mud into hard rock. They used deep cement mixing technology. That means instead of dredging the mud away, which is expensive and polluting, engineers use specialized ships to drive giant drills deep into the seabed. As they drill, they inject high-pressure cement directly into the ground. The cement mixes with the mud right there and hardens. This process creates thousands of concrete pillars right inside the earth. They pierce down to the hard soil below, forming a solid, load-bearing foundation at the bottom of the ocean to support the tunnel. But with the foundation ready, how do you build the tunnel? You cannot pour concrete directly underwater because the current and salt water would destroy the structure immediately. The only solution was build it on land, then bring it to the sea. So on a nearby island, they built a massive factory to start the production process. At this factory, the tunnel is divided into 33 segments, each 180 meters long. The process starts with the skeleton. Instead of using human labor, they use automated robotic arms. These robots bend and tie millions of steel bars with absolute precision to create the load-bearing steel cage. Then, the steel cage is pushed into huge hydraulic molds to pump in the concrete. This is when the biggest risk appears: temperature. As such a massive amount of concrete hardens, the chemical reaction generates heat up to 50 degrees Celsius. High heat inside meeting cold air outside will cause the concrete to crack. To stop this, engineers installed a circulating cooling system right inside the mold. Thousands of cold water pipes are woven between the steel layers. During the casting process, cold water runs continuously through these pipes to cool down the concrete from the inside. Thanks to this three-step process, They created tunnel segments weighing 80,000 tons, smooth as a mirror and without a single crack. Making them is one thing, but moving them out to sea is another. They sealed both ends of the segment with steel walls to turn it into a giant, hollow submarine. Because of this, it can float and be dragged out by 8 tugboats. At the site, they pump water into tanks inside the tunnel. The increased weight makes the tunnel sink slowly into the trench with millimeter precision. But how do you connect 2 concrete blocks underwater tightly without using bolts? The answer is using the power of the ocean itself, hydrostatic pressure. The end of each segment has a giant rubber ring called a Gina gasket. When 2 segments touch, a pump sucks all the water out of the space between them. When the water inside is gone, the pressure in the gap drops to 0. Meanwhile, outside is millions of tons of ocean water pushing down. This pressure difference creates a massive, natural force, pushing the new segment tightly against the old one. The joint becomes completely watertight. This water pressure process worked perfectly for the first 32 segments. But for the final segment in the middle, they faced a trouble. Because both ends were blocked by previous segments, there was no space left to use water pressure to push the final piece in. The solution was the V-shaped joint. They built a special wedge-shaped segment. After lowering it into the gap, instead of water power, they used giant hydraulic jacks inside to push the walls out to the sides, locking the entire tunnel structure into one solid unit. Structurally, the concrete dragon was finished. The steel walls were removed. But a concrete tube underwater is not a safe place for humans yet. It needs life support. They installed jet fans on the ceiling to constantly provide fresh air. Most importantly, the escape route. Every 500 meters, there is a door connecting to a safety corridor. In case of fire, drivers can escape in just a few minutes. Finally, automated inspection robots will crawl along the tunnel walls 24/7 to find the smallest cracks, ensuring the structure lasts for 120 years. The HCMB project proved one thing. When standard machines like the TBM fail, engineers are forced to reinvent the process. From cooling concrete to prevent cracks, to using the ocean's own pressure to build. They turn the impossible into the possible, cutting travel time from 4 hours to 30 minutes and changing the engineering map of the world forever. Would you dare to drive through this tunnel? Let me know in the comments.